So yeah, good evening. It's morning here by me, but good morning, good evening, everyone. So as Linda mentioned, I'm Jonathan Meyer, and I'm the director for Anvil Sparks Modeling. I previously used to work with a few pharmaceutical companies, Pfizer being the most recent one. Really as a role of process modeler. And what I thought to do was, let me just move to the next slide, is to give a talk about something that's an area that I've kind of prior experience in, bringing process models more into the manufacturing environment, and it's really the concept of using state estimation. So it links more into the sort of control systems engineering side of things. And this is my sort of view in terms of when talking about digital twins and essentially process models and bringing those models, alive or online during manufacture to give some sort of an online measurement or so-called soft sensor estimate of the process. And the technology that's typically used in control systems is state estimation. So what I thought to do is spend a bit of time and walk through what is kind of digital twin to me, and also what's out there in literature, what is state estimation, and how we can use this in this case a continuous drug product manufacture example. So basically, what I broke down the agenda is really to talk about, the concept or the what the definition could be of a digital twin. Going a bit more into dynamic process models, which is something that's more, say, related to continuous manufacture, but also comes more from the control systems engineering field. And yeah, so I thought to kind of go through a little bit of that and discuss some of the concepts of what is dynamic, dynamic model, what makes it dynamic, because that's really important for state estimation. It's necessary if one wants to apply or use state estimation, for these dynamic models to be run, say, online. Then what I thought to do was give a case study or an example of how the state estimation could be used in a continuous segmented fluid bed dryer. And then basically just a summary overview, and obviously any questions, welcome to, I'm good to answer them. All right, so I think before we start, Linda mentioned that I could ask a couple of poll questions throughout the presentation. So really it would be nice to get an indication of what your understanding is of the various concepts as I kind of work through it. So so I think she shared basically a poll question that should come up on your screen. And so this is the first question. So what is your understanding of the term digital twin? Is it a mathematical model of a manufacturing process, a 3D virtual representation of a shop floor production area? Is it all data generated from a physical process, or is it a process model that runs online during live operation? I think we can give a minute or so for the respondents to answer, and then there should be a result summary that should come up.
Isn't it all of them?
Yes, I can see that we have a results summary of all of the answers. So it looks like 80% actually responded the last one, which is a process model that runs online during live operations. So I'm very pleased that people have responded that, because that's really how my interpretation is of a digital twin. Is something that a process model that will run live. I think there are some people that responded with the data that's generated, and that's also true. And then also mathematical model was another response. About 80% was really, sort of seeing it the way that I see it, which is a process model that runs online. So that's good to it's good to know. All right, so moving on. So the next slide is really this is really a definition that's from Herwig et al. Their book on digital twins, and I thought to bring this in here because I see that this gives quite a nice definition of a digital twin, and I think kind of thinking back to those questions that I asked, it's really got sort of three core components to it, and the first one is sort of in the middle of the diagram, which is really, it's an in silico and a connected replica of an existing physical asset. So it's really around that, in silico sort of model of the asset or of the unit operation. Then there's the other core component is that it's a virtual or digital asset. So it's kind of a virtual representation, of the physical system. And the sort of the other really important aspect to it is the bidirectional connectivity. So it's really then around the communication that where this digital asset can interface with the physical equipment itself. And that's really like we're talking more about the data and the interface between, the process model and the data that's coming from the physical system. And so obviously these process models can be used in kind of two applications. The one is really, for production purposes. So on the left-hand side, showing, it's live for production in terms of optimization and control. And then on the right-hand side is the R&D environment where, these models are still online, can still be used as digital twins, but are more so used to collect data from the experiments or from the equipment and, provide insights in terms of virtual experiments. So there's really two kind of areas of application of the digital twin. So hopefully that kind of, I think that gives a very nice definition of a digital twin and sort of what are its three kind of core components and applications. Then the next part, what I wanted to really delve a bit more into is now when we talk about like process models and digital twin, one of the areas is, what type of model are we talking about when it comes to digital twin? And when I think about like the digital twin in terms of its online application, I'm thinking more in terms of dynamic models, right? So really models that are described by ordinary differential equations. And you can sort of see on the diagram on the right-hand side what the dynamic modeling or simulation scope is compared to, for example, often, a lot of models that are also used in development and design of processes would be more sort of steady state models or static models. So really the comparison between the steady state model and a dynamic model is basically that the dynamic model is looking at the time evolution of a variable. So, you've got a lot more information that this model is actually incorporating versus a static model or a steady state model is really a single point at over an extended period of time once the process has reached kind of a stable operation. So it's reached, say, steady state. So yeah, so basically the steady state operation is really that kind of like end point in terms of once the process is stabilized, and that's really all what one is trying to predict in terms of a static model or steady state model. Whereas a dynamic model, because of its use of, say, ordinary differential equations, it's not so much, yes, the steady state is there because ultimately that's, what the model is predicting over the extended time horizon. But it's actually really more interested in what is that sort of understanding of the rate of change of those process variables, or the dynamics of the process as it evolves over time. So it's almost like what it's giving us is a more sort of detailed description of the process, as it evolves over time. And I think if I can use a pen here, I can try and sort of draw a diagram maybe. Where's my cursor now? Sorry, it's not now showing. Oh, okay, there it is. So one of the ideas behind, when considering dynamic models is that normally, if you have sort of an example over here, you have quality versus something like, throughput. You'll have maybe like an inverse relationship like this. So the more sort of, say, throughput you put through the system, in a pharmaceutical case, maybe, you're trying to get more flow through a system, that could like impact the, say, quality of the tablets that are produced, maybe the RSD of the mass, or something like that. So there's normally an inverse relationship between the quality and the throughput. But now, if you draw this diagram with a sort of a third dimension over here, which is time, what that means is that you can actually push this envelope of this quality throughput relationship, to a sort of a more optimal condition. So you can sort of eke out more from your process, really just by having the ability to know, what are these sort of process dynamics? How is this process changing over time? And then obviously, use it in some sort of a feedback loop or optimization. And that's really for me, that's really the core understanding behind having a dynamic model and the benefits behind it, from a control systems perspective. So, I mean, other sort of typical examples here are, using these dynamic models for process design purposes and enhancing the optimization of the process. As we sort of mentioned, digital twin, but also utilizing these models of almost like a connection of different systems in series or in parallel, so-called plant-wide or end-to-end models. So sort of building more of a systems sort of engineering approach to modeling a full production line as opposed to a single unit operation. These dynamic models can be used also in the batch processing environment if you want to start getting, more sort of higher definition, say, control of what's happening within the batch process itself. For example, obviously, as I mentioned, process control strategies. Another very important area, actually a very big area where you can gain, thinking about this quality throughputs kind of optimization, is really around the startup and shutdown procedures. And if you can get your dynamic model to capture, those dynamics of what is happening during startup and shutdown, one can also then apply these optimization process, tools over that to get a sort of accelerated startup or, minimize the amount of material that's rejected and that sort of thing. Again, another area is operator training. So that's also, I think, a core concept of digital twins and, allowing operators to have a sort of a screen that they would have very similar to their SCADA system of the current equipment, but in the background you're running one of these dynamic models, and operators can then practice startup, shutdown, what if scenarios, that sort of thing. And then, yeah, another area is more safety analysis. So, I mean, this is more, say, testing the sort of boundary conditions or extreme conditions of the process as such. I think in other industries, safety sort of more also talks about like interlocking and, certain logic around the process to, you know, protect a gas leak or something like that, or an explosion. But you know, that's also another area where these models can come into the application of the design of safety. So that's really, in a nutshell, how I would kind of see dynamic models and really what they entail, and what the sort of benefits are there. Okay, so hopefully that's given you you know, a bit of a good explanation of process dynamics, and so there's a couple of more questions here just to sort of see what your thinking is around it. So the question that's come up is, what makes a dynamic model different to a steady state model? The first one is the output of the mass energy momentum balance equals the input. It consists of ordinary or partial differential equations. It does not contain an initial state. It uses a system state of unknown or known parameters. And then it's we've got either number 2 or 3. So consists of, you know, differential equations, or it doesn't contain an initial state, or 1, 2, and 3. That's then including the energy mass momentum balance of the output must equal the input. So we can just give a couple of minutes, or a minute for this. Be interesting to see the response here. Okay, so here we've got the poll results. And so I can see a lot of people have, actually 75% have actually said 2 and 4. So yeah, so actually that's that's basically where we're saying it consists of differential equations. And okay, the system state of unknown and known parameters. So my interpretation of, you know, dynamic model would definitely cater, or, you know, be an indication of it having differential equations and unknown and known equations, and a system state. So that's definitely in my mind, like I would see that as a correct answer, and I think majority of the people have actually indicated that. Interesting, 17% say yeah, it purely just uses a system system state of unknown or known parameters. That's also true. It's just, I think the key thing is the, you know, definition of the system using ordinary or partial differential equations is quite key. And then a couple of people have also mentioned that number 1, 2, and 3. So in that case, yeah, when we're talking about the model, so basically that the output equals the input, that's actually more when you're looking at the dynamic, the steady state response of a dynamic system. So you're making those differential equations equal to 0, and then you're basically defining a steady state sort of definition of the system. So that's not really then in the sense dynamic, actually. I think that's really the key difference there. And also number 3 would be does not contain an initial state. So yeah, your dynamic model, you know, essentially what you're doing is when you're trying to you know, calculate the result of the differential equation, typically you would need an initial condition. So you know, initial state is actually necessary for one to be able to, you know, use these models, say, in an online fashion. So thank you for the response there. I think majority of the people then really do have a good grasp of what dynamic models are. So again, I won't then go through all the details of then the dynamic model and what it is, but what I then wanted to do was kind of move a little bit more into an example of one. So um, in this case, the application that I wanted to talk about was on a fluid bed dryer, and essentially the kind of dynamic model, say definition would be this green block in the middle here, where mathematically you have an input and an output, and the output is described by some function of the system state, which is x, and the input, and then your differential equation sort of response or interpretation would be this top equation where the rate of change of the state is some other function of the state itself and an input. And so here is an example that I've taken from Liu et al., where they've described the different dynamics of a fluid bed dryer, which is this essentially this diagram on the right, where basically what you do is you would load this dryer with wet granules, and at the base of the dryer you would feed it with drying air, which is at a specific, say, relative humidity and a high temperature. This drying air would basically fluidize the granules in this dryer compartment, and over time you'd get vaporization of the liquid from the wet granules into the drying air, and the drying air would then exit the exhaust, and this is sort of a continuous process of drying within the dryer itself. And the equations that they've described here of this model is really essentially these ordinary differential equations which describe the drying air temperature, the granules temperature of the granules themselves, and then what's usually an area of interest for the prediction of this system is the so-called loss on drying, which is basically the moisture content within the granules and how that moisture content would evolve, over time. So in other words, it's getting less and less and less as it's drying. And all of these sort of equations are interrelated with one another. So this would be a typical example of a dynamic model, in this case for a segmented fluid bed dryer. So once you've got your dynamic model and you've got your equations that are defined, of the system, the next sort of area what I wanted to discuss is more starting to lead into how to bring a dynamic model, as an online measurement or a soft sensor. In this case, want to kind of lead more into the idea around state estimation and why we would want to use state estimation. So what I've sort of described here is the idea about expectation versus reality. Now, obviously, you've got on this diagram on the top, you've got your input to the system. So this would be, your drying air temperature, volumetric flow, the granules, and the moisture content of the granules. And then obviously all of that data, is kind of describing and measured from the real process. So obviously that goes through the real process is now processing the granules, and you've got sensors which would measure an output that you're interested in, which is in this case would be, for example, your cell temperature, as an example. Now, what you would then do is you would run your model kind of in parallel to the real process if you want to, using the model as a sort of a online estimator, well, an online sort of prediction of an output. And basically what I'm trying to kind of describe here is that there's always this kind of like a delta or a difference between what you measure versus what the model predicts. And obviously, you'd want to initially offline calibrate your model so that you make sure that you sort of determine any unknown model parameters that you can fit the model essentially to some offline data. But then when you want to run the model online, you would still typically get a bit of a delta or a deviation between the model versus the reality. And I'm just sort of showing, some of the figures from Liu et al. In their publication where they've calibrated the model quite well. I mean, you can see in this sort of graph in the middle here at the bottom, you've got your experiment measurement of your cell temperature. This was cell 3 versus cell 5. I'll explain a little bit later with a video on why they took about different cells, because in this case they're using it to simulate a segmented fluid bed dryer. The example I've shown is really just modeling one cell. But essentially what I wanted to kind of highlight here is that you can see the model prediction in orange here versus the blue, which is the experiment. Generally, the model does capture the temperature response. As material is or as the dryer is running, you've got the initial air temperature. When the temperature drops like this, that's basically when they've loaded the granules into the dryer. So the temperature measurement is now starting to measure, essentially the temperature of the granules, and not so much the air. And then as the drying sort of takes place over the evolution of time, the granules are getting heated and heated until you've reached the sort of temperature that you want to achieve for the drying, and hopefully ultimately the amount of moisture content is within your specification, and then basically discharge and reload again. So but what I wanted to kind of indicate is that even though, yes, you've got a model and they've done quite a good job to calibrate the model, there are still these small little deltas between the model prediction and the actual measured temperature. And this is really where state estimation can play a significant role. And what I believe that, if we really want to utilize these models as an online, or in an online fashion, we should really start exploiting the measured data to kind of further optimize how we can apply our models for prediction in an online fashion. And I mean, some examples of these causes for these deviations. Obviously, the model is calibrated, but there's uncertainty in the model parameters. So the model is not necessarily capturing all of the physical phenomena that we have. It's an approximation of the process. There can also be, on the measurement side, so you can also have some error in the measurement, which could also contribute towards this error. There can be a disturbance in the process. Maybe something happens, who knows, in the air, relative humidity. There could be maybe there's some atmospheric, moisture in the air, or someone could maybe knock the equipment, or I don't know, there could be some sort of a disturbance in the process. And then also sort of like a signal noise, sort of more related to measurement error. But hopefully you can understand a little bit the idea here in terms of that, you've got your model, you've got your prediction, and there's inherently some error between the model and the prediction. It's never going to be perfect. Maybe another sort of key thing, let me just get my pen again. It's difficult for me to see on here, but another important thing is that obviously you've got these differential equations describing the process. And typically what you want to do is you want to integrate this system between a time interval, T0, and T1. And basically the solution to that will basically be, your solution to your variable. This could be moisture content or whatever, or temperature. But basically you're going to essentially be solving this between, x0 and x1. So this sort of talks about the initial conditions of the solution to these differential equations. And this is a very important concept. And this is when we talk about state estimation, this is really what it is doing, because X would be your system state, so it could be temperature, that sort of thing. And as you're kind of integrating this over each time instance, you're receiving a sample that's measurement from the process, and that each sample is basically a time instance, and you're really then integrating between that current time instance now and the next second or millisecond or whatever frequency you're integrating this system over. And that's really where state estimation plays a role, in that you can try and improve that initial state estimate based on the measurement data that you already have, so that you can get a better prediction in the next instance. And this is basically where Kalman filtering comes in. And the idea behind a Kalman filter is really, is to try to utilize the information that you have at the latest, time, step that you have, and apply a sort of a feedback loop between what you've measured versus what the model is predicting, and sort of optimize in terms of what is that next best guess of that initial state that you want to use in solving that differential equation for the next sort of prediction, for the next second, and sort of so on and so forth. So the Kalman filter was developed by Rudolf Kalman, and this is used in other industries as well, like in aviation and that sort of thing, where like GPS, and so it's a very well known tool that's used to bring sort of mission critical systems, where you need to use a model to control the process, but also then the model has to be a very accurate representation of the process, but also you want to make sure that the model is aligned with your current state or your current measurements of the system. And so the concept here is basically, as I mentioned on the diagram of the bottom left, again, you've got this example of where you've got your model versus your actual measurement. And again, you're using that sort of information with an observer or a state estimator to update that model state. And then the sort of algorithm that Kalman has described here is a two-step process. So on the diagram on the right, you've got on the left predict, and that's essentially where you're taking in that delta t, or that time instance, where you've got your initial condition that you're using in your differential equation to solve for the next prediction. You perform that calculation. That prediction basically gives you like a predicted state and an uncertainty. Well, there is usually like an uncertainty associated with that predicted state. So there's uncertainty in the model prediction. Then the next step is an update state, and that's really where the Kalman filter, what it's doing is it's taking that predicted state with also understanding your measurement noise and your measurement itself. So for example, like you've got an actual reading of temperature, but now you've also predicted what the next sort of temperature state is, and there's model uncertainty, and that there's some error associated with your measurement noise. And you can sort of combine that information to basically update your model state and get your next best guess of what actually the state will be. And again, feed that back into the next prediction step. So it's a two-step process of predict and update, and it kind of iterates as you're progressing along in time for each delta t, or each sample that you want to predict. So hopefully that's kind of a bit the theory behind, I haven't delved into too much of the theory, but it's the concept behind Kalman filter, and really the importance of dynamic models to basically enable that. So what I wanted to do was give a
Sorry, Jonathan, I think we can't hear you anymore. Jonathan, can you hear me? Linda, can you hear me?
Yes.
I can hear you, Christina.
Yeah.
Oh,
I can't hear
okay.
Jonathan
I
either.
can hear you.
But we
Okay, so
cannot
we
hear
write the
you.
message.
Just message him.
Okay. Okay, he's not looking at the chat either.
No.
Oh dear.
How do we do it?
Um, are we able to use?
I think he doesn't realize.
Maybe I just stop share screen. No. Oh,
Yeah.
okay.